So that Judgment Day, that movie Terminator, you must have seen, when Schwarzenegger said, "I'll be back." So this is backtracking. Please, sir. So backtrack. So the concept that we are discussing in the recent past, the difference. I mean, in most of the problems we are using recursion. Okay, but the difference is little bit, slight difference. Backtracking is also will be using recursive algorithms. Okay, but where is the difference? Backtracking is basically a brute force method. Okay, so sometimes you might be finding in YouTube and all, they are saying that this is a brute force method. But in brute force method, what happens? Let's say in this tree itself, you can see that it has gone to the leaf node. It has gone to the leaf node. These are leaf nodes. These are called trees. So as I said, everything which follows recursion, better to visualize it in terms of trees. Backtracking, what happens? The idea of backtracking is that it is a brute force method, because you can see that it is actually checking all the combinations. All combinations it is checking out. Okay. So brute force method problem is with the brute force means it checks all the combinations. So time complexity is huge. Backtracking also uses brute force. Slight difference is there. The difference is that whichever node, if it feels that the constraint is not satisfied, that means the goal, the things that we are going to solve, that is not satisfied, it will ignore that node and it will backtrack. It will try something else. This is the backtracking concept. So it also uses recursion. So basically, backtracking is a method for solving problem recursively by making a solution increasingly one small portion at a time, by avoiding those solutions that fails to satisfy the constraint. Constraint in the sense, there is a discussion among constraint like implicit constraint and explicit constraint. That much we are not going. It's not needed. Constraint means the things that are given for the solution. If it is not met, then it will backtrack. This is the difference. Otherwise, brute force method won't do that. Brute force will continuously go and it will check. It will the trees, the search space is more for brute force. But in case of backtracking, there is a limit. In case of backtracking, if it fails to satisfy the constraint of the problem at any point of time, it will backtrack and it will avoid those paths. So the name backtrack was first coined by Lemmer in 1950s. Early authors who studied the process were Professors Walker, who gave algorithmic account of it in 1960, and then Golomb Band, and these professors are there who already studied this backtracking. Okay. So then how it is different than brute force? As I said, initially we started the backtracking from one possible option. If the problem is solved with that selected options, then we will return the solution, else we will backtrack. Okay. So difference is slight compared to brute force method. Another option from the remaining available option. That means it will backtrack, it will check what are the other options available. There also might be the case where none of the options will give you the solution, and hence we understand that backtracking won't give any solution to that particular problem. It is not necessary that all problem will be solved by backtracking. So it may fail also. Okay. So if you visualize it, backtracking, as I said, it is better to visualize it in terms of trees. So what it happens, let's say this is a tree and A to G are some rules and facts we have. Let's start from A and want to reach G. That means this is the starting node and this is the goal node. Okay, so sometimes we call it, this kind of tree, we call it state space. So you say this is the actual solution A to G. This is what we are intent to solve. The path that I am looking for, which is A to G. But this backtrack, guys, how it will work? So when it discovers, so first what it will do? It will start from, so actual solution, the proper path is ACG. That means ACG. This is our actual path. That is the solution of this problem. Let us assume that. So backtrack, what it will do? It will start from the A and then it will go to B. With a recursive call, it will go to B. Okay, no iterative thing, recursive call. From B to D, it will go from after B. It is not a solution because it is not G. Then it will again try and it will go to D. So B to D it will go. When it discovers that D is not the destination, so D is not the actual, this is not G. So it finds that This is not the solution. So what it will do? It will immediately avoid this path and it will backtrack to the previous node. Okay, just simple, like it's like implementation level work, nothing else. And then it will check the right subtree. Right subtree, it is E. It is check whether E is equal to G. No. Again it will backtrack. That means here when it reaches D, if it is also a recursive call, this also is a recursive call. These are all recursive call to solve it. This recursive call, when it will return false. This E also, when it will go to the E, it will also return false here. So this will be false. So both will be false. So both these things will, so B also obviously will be false. So again it will backtrack to A, it will also be false. Then again it will come to C, thinking that it will be reaching G, and then from C to F it will come. It will see that F is also not the solution, so it will backtrack. So here is a recursive call. Here also is a recursive call. This recursive call also will result false. And then finally it will go to D, and it will go to G, and it will find that G is the actual solution. The goal node, actually this is called goal node. Okay, this goal node is like a destination node, and this whole thing called state space. Sometimes it is called, or sometimes it is called search space. These are nothing but search. It is happening searching only. Okay, so once it reaches G, it will find, okay, this is the destination. So the return will be true here, and this return also will be true. So this is true. This is also true, and this is also true. So finally it will recover. It will discover that ACG is the solution. So when it finds G, it stops. That means final call is like that. So this is how this backtrack. So where is the backtrack happens? These dotted lines are backtrack. They go back and go to the original locations. Okay. So there will be many recursive calls here. This is backtracking. So this is a difference. We will be using recurrence relation here also, recursive method. So our first problem is called n-queen problem. Okay. Many of you already might have heard n-queen problem. This n-queen problem is inspired from the chessboard game. So in chessboard, normally we have many things, kings, queens, lot of other stuffs are also there. But in n-queen problem is different. Here we will only be having queens. Okay, we will only be having queens. So considering that we will be having n cross n chessboard. Okay, so this is the chessboard. We will be having n cross n, and here I have taken 4 cross 4 chessboard. So here n is equal to 4. Okay, n is equal to 4. So n queen. What is n queen problem? N queen problem is to place n queens in such a manner of an n cross n chessboard. That means 4 cross 4 chessboard, that no queens attack each other. By being in the same row or same column or diagonal. That means if you place your first queen here, let's say this is my queen 1, then you cannot place the queen horizontally here, or you cannot, let's say this is your first queen, you cannot place anything in this column, neither you can place these queens here, neither diagonally. Okay, so this is the, so where you should keep your second queen. If you keep your second queen here, then you will be thinking, okay, this might be a result. So there will be recursive call. Then third queen, where you can you place here third queen? No, you cannot place. Can you place here third queen? No. But then fourth queen you are not able to place anywhere. So this solution is also not giving. So what to do? So one of the solution, you may have more than one solution. One of the solution of this problem is if you place first queen, it might be one of the solutions. Okay, but this is okay. But we have to use backtracking method to solve this problem. That is the intention. So this is n-queen problem. In fact, this is a 4-queen problem. We can call it 4-queen problem. Okay. So this has to be solved by backtracking. You can solve this problem using dynamic programming also. You can solve this problem using dynamic programming also. Maybe, I don't know, greedy method and all other things you can try. But here our intention is to do it backtracking method. Okay. This is n-queen problem. So you can see that. So you have to generalize this thing and then you have to proceed. What is the generalization? First thing is that, let's say, actually when the problem happens, let's say you have placed the first queen. Second queen, when you are placing, you have to check that whether second queen is attacking first queen or not. Let's say you have placed first queen and second queen both, or 0th queen or first queen you have placed, third queen you are going to place. You will be checking whether third queen is attacking 0th queen and second queen is attacking 0th queen, or first queen or not. Similarly, when you are placing, if let's say we have 0th queen, first queen, second queen, third queen, we have 4 queens. So when you will be placing third queen, you will be checking whether it is attacking 0th queen, first queen, second queen and third queen or not. So what are the options we have? Let's say we are placing our queen here in the, this is a matrix of 4 cross 4 chessboard. 1 and 2 we have placed. Okay. So for this 1 and 2, which are the squares that under attack, that you have to find. And you have to find whether there is a similarity between that, so that we can have a recursive method on it. So this queen, the queen that we have placed is actually your 1 and 2, because we have indexed it 0, 0, 0th column, then first column, second column, third column, 0th row, first row, second row, third row. So let's say row wise we will see, column wise we will see, diagonal wise we will see which are the options are there, which are the possibilities are there that the queens will be under attack. That means the existing queen will be under attack for this queen that we have placed here. Okay. So for that, if you see minutely, row 1 0, 1 1, 1 3, these squares, that means the queens, if the queens, existing queens are already in these indexes or this column row column values, they will be under attack. That means, what is that? 1 0, that means 1 0 means row 1, 0th column here, if it is there, it will be under attack. Then 1 0, then 1 1, if it is in 1 1, that means this cell it will be attacked. Then if it is in 1 3, row wise 1 3, 1 and 3, here also if it is there, it will be under attack. This is row wise we are trying to do. That means all the row which are 1 1 1 will be under attack. Okay, because here 1 1 1 rows are equal and the columns are varying, no problem. This is row wise we are looking at it. What about the column wise? Column wise you can see that all the columns which are 2, yes, all columns, the queens that are already in columns 2 will be under attack. So that means 0 2 2 2 and 3 2 and 3 2, these all things, these all squares, existing queens which are here, here, here or here will be under attack. Now diagonal wise also there is a threat once we place this queen. So what we will do, which diagonal we will be trying to see, all squares which have the same values of the queen's row will be under attack, which is 1 0 1 1 1 3. Similarly, all the squares which are of the same column value of the queen's column, that means here if you see the queen's column which is first row 1 and column 2, these things row wise these guys are under attack, column wise these guys are under attack. Okay, now we have 2 types of diagonals threat. One diagonal threat is from left, top left to bottom right. That means this kind of diagonals also we have a problem. This top left to bottom right, these diagonals, one type of diagonals. Another type of diagonals which is bottom left to top right. These 2 types of diagonals, squares, where if the queens are there, then also you have a threat. That means diagonal 1, that means top left to bottom right, 0 1 2 3, 0 1, that means this guy, and 2 3, that means this fellow, top to bottom, top left to bottom right, these squares are also under threat. Okay, we cannot place, I mean if you place queen here, then these queens will be under threat, under attack. And the other diagonal 2 we are calling it, which we should be considered from bottom left to top right. Those guys are like 3 0 2 1 and 0 3. 3 0 2 1 means row 3 3 0 here, this one and this one. These 3 fellows also will be under threat or under attack. So these are the options we have. So basically to find the first type of diagonal, we will follow one formula which is row minus columns. First type of diagonal in the sense top left to bottom right wala diagonal, that will be row minus column value. We will subtract the column value from the row value. If it is -1, then the first type of diagonals will be evaluated. So let's say queens are in 1 2, that means 1 minus 2, if it is -1. By this process we will track those guys. And for other diagonal we will add row plus column. If it is row plus column equal to 3, then also it will be under threat. So if in case of 4 queen problem, 1 2, if -1, row minus columns, and row plus column if it is 3, that means those diagonals also will be under threat. Now let us do the recursive part of it. Okay. So basically, what we are having 4 queens. The queen that you are placing, she will be attacking those. Now let us do it. You will understand. It will be fun. So let's say we have. So first of all, let us draw this thing here. So this is 0th queen. This is first queen. This is second queen, or this is third queen. Or what we will do? We will use backtracking. So how to proceed? So at 0th level of recursion, we will place the 0th queen on the 0th row. Yeah, at 0th level of recursion, we will be placing 0th queen. That means first queen on the first row. Okay, so first queen on the first row. So we are placing it first queen. Let us make it black. So 0th queen, by definition, we will be placing it to the 0th row. That means here we will be trying to place it here, and here also we are going to place it here. Okay. Next, first queen. That means 0th queen has been placed. Next, first queen we are going to see. That means the second queen. So second queen, as it is recursive, let us have, because it will go as a tree fashion, nothing else. So let us draw these 2. So index is 0, 1, 2, 3, 0, 1, 2, 3, 0, 1, 2. That means second queen we are going to place. We will be trying to place these queens row wise. If it is possible, that is our intention. By this process, if you find that it is attacking, then we will try to place it to the next possible location that is available on the row itself. And then previous placement where we have placed our queen, that will be false. Recursive call will be false. So next, we are going to place our first queen, first level of recursion we are going to place. So we are going to place it. Where should we place? If we place it here, it will be attacked. If we place it here, it will be under attack. If you place here, then okay. So let us place it here. That means, and also you maintain the indexes. Initial index is 0, 0. Second index is 1, 2. That means third location I am going to, so recursive call has done. One recursive call. And it has been placed at second position. Okay, this is there. Yeah. Now we are trying to place second queen, that means third queen on third row, and we will check whether any attacks happens or not. That means it is better to have a So next we are going, so this guy will call a recursive call. Okay. So now second queen, that means third queen, we will be trying to place it at that second row, that means third row. But if we place here, it will be under attack. If you place here, it will be under attack. If you place, it will be under attack. Anywhere you apply, it will be under attack. That means, although the recursive calls happens here, but the return will be false. Because second row, that means third row, you are not able to place the queen. So what it will do? It will do nothing. It will check its right subtree whether any other options are there to place. That means, okay, by this process, as it is false, you just delete this index, I suppose. Delete this index, and then this 1, 2 wala things has gone. So we will place, that means this is a false thing. So you place second queen on last location here. So that means second queen will be, so this queen has been gone here. It will be placed, I am right or wrong? It will be placed here, and then this guy will call a recursive call. And now we are trying to push this second queen again to that means second row, that means 0, 1 to third row. So third row, I think you can place it here, correct? Third row you can place it here. Now this index is nothing but 2, 1. 2, 1. That means here we are trying to place our third queen. So index is also there, 0, 0, 1, 3, 2, 1. Now we are now the third queen you are going to place. That means the fourth queen you are going to place. So fourth queen, let us have a. There is no harm of trying this. Now fourth queen you cannot place anywhere. So the call will be there, recursive call, but it will be in vain. That means this location, this square is under attack. This square is also under attack. Similarly, this also under attack. This also under attack. That means this call that you have made, recursive call, that is a false call. That means we cannot place anywhere the fourth queen, that means third index third wala queen you cannot place anywhere. That means this also will be false, which in turn will suggest that this also will be false. Yes or no? So this, first of all, this, okay, so here nothing place is happening. So 2, 1 that we have done here, this also will be a false call. This will also give a false call here. False call. Now the interesting thing is that this fellow, the first queen, that means the second queen, first index wala, has been already placed in the last location. It doesn't have any choice. So it is also in vain. It is also a false call. So this guy also will return false. So every time I am just, whenever it is false, it is backtracking. Backtracking. This is also backtracking. This is also backtracking. Now it does. That means it is a failure. The choice of this 0th row and 0th column is this also false. This also false. So this is false. Now you have to try the second portion, second location available. That means initial call becomes that means all the left subtree calls are false. It has forced the first recursive call to place the first queen, 0th queen, second position. That means now we don't have any choice. As I said, it will be going through row wise. You have to place it here. Once you place it here, this thing will change. So this guy will give a, so here you have Q. So that means my new index is 0, 1, 1. First queen, 0th queen placed. And second queen, I can place. Can I place here? No. Can I place here? No, it will attack. Can I place here? No, I can place it here, second queen. So first, so okay, so that means 0, 1, 3. 1, 3 is my new index. 1, 3. So that means here my first queen, and this fellow will again call. That means now I'll be trying to push the second queen, that means second index queen, that is third queen. Where can I push? I can push it the second row, 0th column itself. I can place it. It won't attack anyone. It won't attack anyone. It won't attack this. It won't attack this. So that means the second index call recursive. So this is a recursive call. This is a recursive call. So this guy will be placed at here, 0th location, which is nothing but 2, 0. 2, 0. And then now I am going to place my fourth queen, which is the third index queen, row index. I can place it very well here. Okay, which is nothing but 3, 2. 3, 2. So this is my 3, 2. So again another call will be there. Call 3, 2. That means third. Now once it comes here, nobody is attacking each other. So this return will be a true return. This return also will be a true return. This return also will be a true return. Okay. So we got the result. The final indexes are 0, 1, 1, 3, 2, 0, 3, 2. Now time complexity for this 4 queen problem or n queen problem is huge. because every time it is making a tree. In fact, it is factorial n. I can have n branches, factorial n, and it is polynomial. I mean, it is exponential. Instead of saying factorial n, it is not exactly factorial n, but near to factorial n. So exponential is the time complexity, provided that the number of the order of the chessboard is within the limit. We will be able to find it. When 8 cross 8 also will be able to find it. But once it grows, then it is not possible. It will actually it will exponential time complexity, and space complexity. Space, we just take 4 recursive call. So n queen problem will take n recursive call. So space complexity is O(n), and time complexity is near to factorial n, which is exponential. So this is n queen problem. Today our topic is subset sum problem. Subset sum, or sometimes it is referred as sum of subset. Subset sum or sum of subset, that means we have to solve this problem. That means we can write it like this: solving subset sum or sum of subset problem using backtracking. So set theory, most of you know what is set. So basically the problem statement says that given n distinct positive numbers usually called weights, we have to find all combinations of these numbers whose sum adds up to given number. That means one number will be given, you will be having subset, and then you have to find which subset actually giving total number. So very common problem, subset sum problem. So basically this is again a search strategy only we have to use. So one way to find subset sum of M is to consider all positive subsets, that I am not writing. So basically what you have to do, we have to create a power set. A power set contains all those subsets which one? Given number. Numbers will be given in the set. Then you have to get the subset. One another summation number will be given, that you have to see which are the subsets adding up to that number. So those number you have to display. That is a subset sum problem. Okay. So a power set containing all those subset generated from didn't get the time for preparing PPT. So generated from a given set. Okay, so first of all, we have to understand what is power set. So let's say numbers are, sir, please sir. Let's say numbers are given as 1, 2, 3. So you know that if 3 numbers are given, we can create 8 subset. So what will be the subset? First is 5, 1, 2, then one combinations 1, 2, 1, 3, 2, 3, and then finally 1, 2, 3. So these are the subset. Okay. So basically, if 3 numbers are there, then we have 2 to the power 3, 8 combinations. So if n numbers are there, then 2 to the power n is the total number of subset that will be created. So basically, this is the time complexity. Even if you use backtracking, brute force method, this is the time complexity, 2 to the power n. Now, what we are going to do? So I'm just saving it, so that later on, if it is needed, we will. Shall I rub it, Professor? Okay. Our set just created. Now, one small example we'll see, and then we'll see how to solve it using backtracking. So basically, what we have, let's say we have this set 1, 2, 3, 4, 5. 5 numbers are there, and the sum that we are looking at 8. So which of the subset will add up to this 8? That is a problem statement. So basically, 1, 2, 5. This is one set. 1, 3, 4. This is another set. 3, 5. This is another. So 3 combinations we have, and they are adding up to 8. So you have to find these subsets. Okay. So what is the procedure? Procedure is that we have to create a search space tree, which will be like this. So this is state space tree, actually, state space tree. Like every time you are creating, because this has to solve it using recursion. So every node will be having right child and left child and right child. So if we consider the element from the set, given set, first element, let's say I'm considering, so in the first level we will write x1 equal to 1, and if you are not considering it, then we will write x1 equal to 0. Like that, this tree will move. In the second level, if we consider the x2 equal to 1, and if you not consider x2 equal to 0, like that tree will grow. But the problem is that like this, if you see, then it is the time will be huge. So it's a brute force method. So for that, we have a bounding function, which will limit this brute force like situation. Bounding function. Just I'm rubbing it. So bounding function is what? Yes. Again, I'm going to write bounding functions. Next. The bounding functions, which is, first of all, let's say n distinct positive elements. The bounding function 𝑏𝑘 x1, x2, let's say k number of weights we have, is true if we have summation I goes to 1 to k. Sir, please, sir. 𝒔𝒊𝑖 𝒔𝑖. That means if you consider x equal to 1, then weight will come. Left, children. If you consider xi equal to 0, we won't consider that weight. So there will be situation when this part could be 0 if you are not considering it. So for that, another summation will be in place, that is wi, where I equal to k plus 1 to n. Okay, such that it should be greater than or equal to m. What is m? M is the weight that we have summed. Okay, that you know. So here, for a node at level I, so I can write it here. First we are giving the basic, then we will solve the problem, not an issue. For a node at level I, the left child corresponds to 1, left child corresponds to 1, and then right child corresponds to 0. Okay. Now one thing is that here this x1 to xk cannot lead to an answer node in this condition, which is true. X1 to xk, this guy not necessarily always will give you the answer. So what we are going to do, it should be greater than this is no, this should be greater than n. This is we have started, we have to modify this function. This we have started, we are thinking like that. This part will, if xi is 0, then this part will be 0. So the right part will be giving the answer, and then it should be greater than or equal to m. This is first we are starting with the bounding function. The bounding function will be having some constraints, some changes. So you just write it. We'll come to it. In this case, x1 to xk cannot lead to an answer node if summation I equal to 1 to k 𝑤𝑖𝑥𝑖 plus 𝑤k plus 1 greater than or equal to m. Okay. If both together is not able to give you the answer, so this will be a false statement. The bounding function we use are bk x1 x2 up to xk is true if and only if summation 𝑤𝑖𝑥𝑖 I equal to 1 to k plus summation I equal to k plus 1 to n, because we have total n numbers, wi greater than or equal to m, equal to sign has come, and another condition which is I equal to 1 to k 𝑤𝑖𝑥𝑖 plus 𝑤𝑖k plus 1 less than or equal to m. Okay. Sorry, less than or equal to m. Yeah, it will be matching. Answer is matching. Okay, this is the mathematical functions. Meaning is that the layman point of view meaning is that these two conditions will satisfy if the left child also true sometimes, if the right child also true sometimes, combined will get the answer. This function says like you can visualize the subset sum problem in terms of this diagram, where you can see that this might be level 0 and this is level 1. Like that, this tree will enhance further. Obviously, we will be using the recursive algorithm. So basically, this is wy is the total weight. That means the sum that the subsets will be adding up to. We have three elements, which is 2, 4 and 6, and the summation, that total addition that has to add up to, let's say, 6. Simple example. So basically what happens in the first level, we have this where the index is, the initial wi xi, which is initially 0, and this is index k, this is total weight of this three elements, which is 2 plus 4 plus 2 plus 4 plus 6, which is nothing but 12. Here it will be 12. So first level of recursion, where either we will choose x1 or you won't choose. Let's say we are choosing x1, so x1 will be equal to 1, and x1 this side it will be equal to 0. So here you can see that what will happen. The formula says that wi(xi) plus wk, left hand side. That means if we are picking this 2, which is 0 plus 2 equal to 2, 0 plus 2, and k will be incremented by 1. Initially k will be equal to 1, so 1 plus 1 2, and this total weight 12. Once you add it, then it will be wi(xi) minus wk, wi(xi) minus wk. That means we have chosen 2, so 2 will be subtracted from 12. That's why it will come 10 here. This is there. Next, let's say at second level of recursion, we choose x2 equal to 1, here x2 equal to 0. So what will happen? That means the second element, which is nothing but 4, let's say we are choosing it, will be 2 plus 4 equal to 6, and the index, the index k will be incremented by 1, which will be 2 plus 1 3, and okay, so here and then you have 10. From 10 you have to subtract 4. That means it will be 6. So here you can see that this wi(xi), which is matches up to 6. So this is solution 1. We got the result, solution 1. Now if you go further, if you add further, let's say 6, here it is not needed, actually got the answer. So it will be backtrack, and the resultant will be true. I mean the return value will be true, and it will be return value will be true. Is there. Now this is there. Now if you don't choose this one, if you don't choose this x2 equal to 1, that means if you don't choose the second element, which is 4, what will happen? As I said, here it will be not choosing it. So basically so whatever is there, the wi(xi) will be as it is, and this will increment. Obviously k will be k plus 1, 2 plus 1 3, and the subtraction will happen because you are ignoring 4. Obviously 10 minus 4, which will be equal to 6 with there. So this is there. Next, if you choose the third element, which is 6, let's say, so in this case x3 equal to 1, and in this side x3 is 0. So if you choose x3, let's say, so it will be choosing, so 6 plus 2, which is equal to 8, 3 plus 1 4, and 6 minus 1 0. Now here is a violation of bounding function. Here is the violation bounding function, because it is 8 now and are given sum that has to add up is 6. So it will kill the node, what it called kill the node, or you can call it backtrack. This return will be false, and this side let's say this side not choosing 6, it will be 2, 4, this reduction will be there. So there also no way that 2 is matching up to 6. This return also will be, and it will backtrack. Here also backtrack, here also backtrack. Fine. Now if you would have not chosen this x1 equal to, you would have not chosen the first element, in that case it will be remaining as it is 0. The index will increment to 2, and you haven't chosen, so the reduction 2 will happen because you are ignoring that element, although you are not adding it wi(xi), but you are ignoring this 2 first element. So 12 minus 10, which is equal to 12 minus 2, which is equal to 10, that will be there. Now from here, let's say x2 equal to 1, x2 equal to 0. If this is the situation, what will happen here? So you are choosing the second element. So second element, yeah, so 0 plus 4, 4, and this will be incremented by 1, 3, 10 minus 4, which is equal to 6. Okay. And again, if you choose the last element, is the third element, and let's say that element is nothing but 6. 6 plus 4, 10, and this is incrementing. So this is x3 equal to 1, and then x3 equal to 0. 6 plus 10 equal to 10, and then you have this 3 plus 1, 4 incremented index. So this is index, right? K index is every time it is incrementing by k plus 1, and then 6 minus 6, which is equal to 0. Now again, here you have this violation. So this is L. Violation of bounding function. So it will be, so this is x3 also, it will be false return, no more. So kill the process here. Now this part is just that we ignore the things, so it will be 4 will be as it is, and 4 will be as it is, and here it will be yeah, and then 3 will be incremented by 1 to 4, and 6 minus 6, which is equal to 0. This also not adding up to 6. This process also will be false, return false, backtracking here. Here backtracking happens. Now, if you would have not chosen the third element, it will be as it is 0. 2 will be incremented by 3. Then decrement obviously will happen, as I said, 6. Now let's say you are choosing in the level 3, when x3 equal to 1 and x3 equal to 0, you are choosing this element, which is nothing but 6. 0 plus 1, 6. 3 will be incremented by 1, 4. 6 minus 6, 0. And this side it will be not choosing 0. 3 plus 1, 4, and 6 minus 0. So this will return false. However, this is false, but this one is giving us a true return value. This will be true return value. Okay, return true. This will return true here. Okay, this will return true here. So this is solution 2. This is solution 1. So we have two solutions. You see minutely. So this is x1. This is x1 equal to 0. So first solution is 1, 1, First solution is 1 1, or you can call it 1 1 0, because the choice of the element is 2 4, which add up to 6. And the second case, which is the right subtree, first one is the left subtree, second which is right subtree, which is 0 0, and then this is 1, right? X equal to 1, 0 0 1, 0 0 1 is nothing but 2. I mean, you see here 1 1 0 means this is first one is 1 1 0 means 1 1 0, 4 plus 2 6, and here it is like here it is like 0 0 1. So this is not chosen. This is not chosen. This 6 is chosen. 0 0 1 is also 6. So in this case, we have the subset sum problem. We have given the sum is 6. We have solution, 2 solutions. Actually, you can have multiple solutions in this case using backtracking algorithm, and the time complexity of this algorithm is nothing but 2 to the power n. Time complexity is 2 to the power n. Time complexity is time complexity is 2 to the power n. Time complexity is 2 to the power n, and phase complexity is, because the array size is limited, is nothing but n. Phase complexity, because we won't call the recursive function for already visited element, even though we have traversing the entire array, each subset, height of the recursive tree would still be remain as On. This height is the maximum phase complexity, On. Time complexity will be to the power n. Actually, it is k into 2 to the power n, but k is a number of element in the set, in set, 2 to the power n, which is constant. So this is subset sum problem or sum of subset problem solution of sum of subset using backtracking. Today we are going to start solving graph coloring problem with backtracking. Okay? Solving graph coloring problem with backtracking. So graph coloring problem also you have seen in greedy method. So basically graph coloring problem is a patent problem. Like you will find a lot of theoretical computer science scientists, they work in this graph coloring problem, because it is difficult to color the graphs, arbitrary graph, with minimum number of colors. Okay, it is difficult. That's why this problem is hard problem. It is correct, sir. Thank you. So graph coloring problem is a popular problem among theoretical computer scientists, because it is difficult to colors the node different with different colors, so that node to adjacent vertex will be, actually it is difficult to color. Like in this case, let's say this is red, this is green, so these two are adjacent, so node to adjacent vertex will be having same color. That is the intention. So with that thing in mind, when the number of vertices increases and the colors are limited, that time it becomes a tough problem to solve. Actually, three coloring problem, that means if you are given three coloring problem is NP complete. NP complete, in the initial classes I give you some idea. That means you can imagine three coloring problem is not easy to solve in polynomial time. Okay, three coloring problem, that means given three color, red, green and let's say black. If I ask you to color a graph with ample amount of vertices, you will fail. It will not happen. So three coloring problem is NP complete. Okay. Okay, when the number of color increases more than 3, that time chances are there that we will be able to color it. Actually, total number of total, that means total chromatic. Actually, there is a terminology called chromatic number, which I have written here, chromatic number. So chromatic number is the minimum number of colors that is required to color a graph. So finding chromatic number of an arbitrary graph is a hard problem. Hard problem is not that hard. It is again the unsolvable problem. Okay, but 3 coloring problem, it is proved that it is NP complete. So I think last class 4 colors means you are saying more than 3. So that might be solvable. I don't have that much idea about that. But when number of colors are increasing, that means you have a chance that you will be able to color. But one thing is sure, if number of vertices are increasing means it will become difficult. But 3 coloring problem is NP complete. That means you have to prove that the 3 coloring problem is in NP, and then you have to prove 3 coloring problem is NP hard. That is the thing. Okay. So these are some background, and finding minimum color of an arbitrary graph, that means chromatic number, is again a tough problem. But here we are not, this is just a background. So people used to work on coloring problem a lot, theoretical computer scientist. So what you have to do, we have to use backtracking. That too we'll be using in a very simplistic graph, and we'll see how this backtracking will be helping us to solve the problems of graph coloring, limited vertices, and so that no two adjacent vertices will be having the same color. It's not that much big deal. Actually, people used to check whether the, like this region, let's say this is this region and this region are adjacent or not. So this is, let's say this region is totally red, this is black. So each region you can represent in terms of a vertices. So this way you can actually segregate distinguish the significance of coloring a graph is to distinguish the regions. So this is one of the applications. Okay. So this is 2, 1. So 2 is connected to 1, 3, 4. So this is region wise, and this is graph wise you are representing. Okay. So this problem has been converted to a graph problem. Basically, major application is on region segregation. Now we'll see one simple application using backtracking. If I do some mistake, you will guide me. Let's say we have 4 vertices A, B, C, D. Okay, 4 vertices, and this is the graph we have, and we have given M equal to 3. That means we have given 3 colors. Okay, so each colors are, let's say, represented as x1, x2 equal to 2, x3 equal to 3. These 3 colors, instead of writing, let's say, red, green and black, we will be writing 1, 2, 3. Okay. So what is the criteria? Criteria is that if you are coloring A with red, then B should not be colored with red. It should be either colored with green or black. Similarly, when you color black, C should not be red or so like that you have to go. So basically what happens, you have to make a tree structure, you know that, because all these problems will be solving by recursion and tree. So first we will be having one vertex here. So for the first vertex, which is vertex A, we have 3 options. No, we can color A with 1, 2, 3, any color starting. So let's say we are choosing x1 equal to 1. That means color 1 we choose. That means here we are coloring with 1, color 1. Okay. Once you color this one as color 1, then you are having options for B. There's 2 and 3, write it there. So for B you have option 2 and 3. So x2 equal to 2 and x2 equal to 3. We have 2 options. So this is A and this is B. So fine. Now you have to choose C. So if you choose, if you choose, let's say you are choosing for B, if it is 2, then for C we have option 1 and 3. One and 3. So this is C. Okay. Now if you have, for C, if you choose A, then it cannot be 1, because if you put 1 here, then these two will be having same color. So we can have here 2, and we can also have here 3. So x4 equal to 2, x4 equal to 3. So this is D, this is D. Okay. Now no more further things can be done. So let us check this one when x3 equal to 3. So instead of this one, this one C, if you let's say this is 1 3, so if I would have chosen 3 here, so what are the options for this? 1. Can I choose 2? 1 cannot be there, so 2. Only 2 is the option for this one. Huh? 3 also is there, right? 2, 3. 2. I have chosen, which one I have chosen here? 3 I have chosen, the 3 cannot be there, right? It will be adjacent. No, 1 if you choose means this will be a color, same color. I have chosen 3 here, so it will be 2 only, correct? So this is x4 equal to 2. Now this is, now we have to go to B, so better we can write it here. A, B, C, D. So here it is 1. For B, instead of choosing 2, if instead of choosing, if I choose 3, then C I have option 1 and 3, 1 and 2. So C I have option 1 and 2. So C 1, and if I choose only 1, then for D I have option 2. Also I think I have option 3, correct? So which one? This one, right? This is D. So 2 and 3. So 2 and 3. If I would have chosen instead of 1, if I would have chosen 2, then here I will be only having option 3. 1 I cannot take, otherwise A and B will be having same color. So only for 2 it is only 3. 3. Correct? Huh? C as 1 already we did, na? Here. C as 1 means either you will be having 2 or 3. Here 2 or 3. If C is 1, 2 or 3, no problem. If it is 2, then you can only have 3 here. Correct. Now this is done. Now let us go to this left hand side. That means for 1, if you color the first vertex as 1, then means this tree will be created, which is we have done. Okay. Now that is the criteria, nothing else. Now let us go to the, instead of choosing A equal to, instead of choosing this is 1, x1 equal to 2. If I would have chosen color here as 2A, because this part already I have done. So again A, B, C, D. So what I did, I choose A as 2, color 2, this one. So what are the options for B? I have option 1 and 3. So this is 1, and if you have chosen 1 here as B, so you will be having 2 and 3. And 3. Now if you choose 2 here, then I can have 1. Can I have 3 here? 1 can come, no problem I guess. 1, 2. So 1 and 3. Now instead of choosing 3, if I would have chosen, instead of choosing 2, if I have chosen 3, then I will be having 1. Can I have 2? No, because then marginal. So only 1. So this is only 1. This is D. So you can write it like this. This is x1. This level x2. This is x3. This is x4. Now what happens if I choose B instead of choosing? So here what I have done, A, B, C, D. Instead of choosing 1 here, if I choose 1 is not chosen, I am choosing 3. So I have option here 1 and 2. Correct, sir? 1 and 2. Now here if I choose 1, then I will be having 3 only. That means this part is done. If I choose 2 here, then I will be having 1, 3. Very good. Done. So this part also done. So this middle one, if we choose this one, this middle wala also completed. Okay. Now instead of choosing 2 at A, 2 for A, if we choose 3, then what will happen? Just one second, just I'll erase it. Erase, Professor? Have you noted down? Shall I erase it? Okay, good. Now let us if I choose 3, that means here it is 3. So I will be having 1, 2. One, 2. If I choose only 1, I will be having 2 or 3. If I choose only 2, then I will be having 1. Yeah, then instead of 2, then I can have 1 and 2. Now this is done, okay? Is it correct? Then for B, instead of choosing 2, so if it is 2, then 1 and 3. If I choose only 1, then it will be 2 and 3. If I choose, here, sir, if I choose 1, then here it will be what? 3 I cannot take. 1 can I? 1, 2. Yes, 1, 2. Correct. This part, no. So I have chosen 1 here. So what are the options I have? Huh? 2 and 3, right? No, 2, no, only 1. Only 2, that is done. And this part is 3 I have chosen. So if I choose 3 means 1 and 2. So 1 and 2. 1 and 2. Okay, so this is done. Now if you finally see the things, it will look like this. Okay, so this is the state space tree. Okay. So what is the solution? How many solutions? No, sir. For 4-node graph with 3 colors. So this is one unique solution. This path 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 18 solutions. Time complexity for this graph, will come to it, but the algorithm also little bit will discuss. Time complexity is big O, number of color to the power number of vertices, and space complexity is linear O of n. M coloring, that will see, but 5 node means will become big. Yeah, will become big. 5 nodes. No, this is the horizon Sahani. So here in this M coloring, 2 algorithms are there, two algorithm functions are there, 2 functions. One is M coloring, another is next value. So here you see the recursive call is happening. So initially in next value k, here k will be passed. K means, like in this case 1, 2, 3, 4 vertices, these are all be passed here. Color of M is 3. Okay. Let's say how many way you can color. So this is the next value k. So next value call will be here, from here next value call is going here. And you can see here one, just for each node how many way you can color, that is there. Okay. And this is one interesting thing in this function. G of k comma j is not equal to 0. That means that there is connection between the 2 nodes. This means the connection between 2 nodes. Okay. And if the colors are also same and connection is there, then it will break. That means if both are having same color, red, this is the situation. Let's say this is sk, this is xj. Kj not equal to 0, connection is there. If they are also same red color, then it will break. It won't further proceed. It will try other adjacent vertices. Okay. So this is the algorithm.